The idea behind black holes actually dates back a very long time to the 1780s and 1790s. So there are two great mathematicians, physicists you'd call them now. One of them, the French mathematician Laplace, and the other one, an English clergyman called Mitchell. And they were thinking about an idea called escape velocity, which is the speed you have to travel to escape the gravitational pull of an object. So for example, from the surface of the Earth, you have to travel a quite astonishing 11 kilometers per second to completely escape the gravitational pull into deep space. You increase the size of the object. So go, for example, to the Sun, let's say. The Sun, significantly bigger, significantly more massive. I should say this is a video, a film, a real film of the Sun taken by a spacecraft called the Solar Dynamics Observatory. And if you look very carefully, can you see just below the equator, you see a little dot there, it's tracing its way across the face of the Sun. That's the planet Mercury. So this is what's called a transit of Mercury. It gives you a sense of the scale of a star relative to a planet. You can fit 1 million Earths inside the Sun. 700,000 kilometers in radius. If you got in a passenger plane, it would take you 6 months to fly around the equator. It's a huge thing. So the escape velocity is bigger. It's actually an astonishing, again, 620 kilometers per second you've got to travel to escape the Sun's gravitational pull. What Mitchell and Laplace thought, it's a beautiful idea, is that, well, is it the case then that you can continue to increase the size of stars? You get bigger and bigger, more and more massive, until the escape velocity at the surface exceeds the speed of light. And then you wouldn't be able to see it. And Laplace, in his paper, this beautiful paper, he says that the largest objects in the universe may go unseen by reason of their magnitude. So it's a lovely sort of idea. You can imagine that he was imagining dark stars, as he called them. Now, we know now that such stars do not exist, stars that massive. However, it turns out that you can increase the escape velocity at the surface by also squashing something down. It's kind of paradoxical. And it turns out that if you take the Sun and squash it down from 700,000 kilometers in radius to 3 kilometers in radius, squash it down, then the escape velocity at the surface exceeds the speed of light, and that is essentially the modern idea of a black hole. For the Earth, by the way, it's about that big. Right? Squash the whole planet down in something less than 1 centimeter in radius, it would trap light. Now, that idea that a star can form such a thing was, theoretically, it was understood. It goes all the way back to Einstein's theory of general relativity, published in 1915. But I think it's true to say that most physicists at the time, Einstein included, felt that even though you could imagine such a thing, theoretically, it would not form. There would be some sort of process. At the end of a star's life, maybe the star collapses and then bounces and all the material goes away. And a star never collapses into something that small. Arthur Eddington, great physicist, said, nature will prevent such absurdities from existing. He dismissed it. And we now know, though, that stars, very massive stars, more massive than the Sun, do collapse without limit at the end of their lives and trap light, form black holes. Now, we know that because we've seen them. We have photographs of them. But the theory, Einstein's theory, predicts that if such a thing happens, then very odd things happen in the vicinity of a black hole. In particular, Einstein's theory predicts that if you can collapse a star in that way, then there is a point in space, a place in space, just over there, you could imagine in this room, a place in space where time stops. It's a direct prediction of the theory. Collapse a star, there's a place where time stops. And even worse than that, stranger than that, inside, the theory predicts, lurks the end of time itself. It's a very strange prediction, which is why most people felt that nature would not create such things. Now, we know that nature has created such things. This is a simulation of what a black hole would look like. The interesting thing about black holes in Einstein's theory is that they are essentially an imprint in the fabric of the universe. It's as if you took the star away, but left its imprint in space and time. Pure geometry, the description of a black hole. And this is a simulation using Einstein's equations to fly up to and into orbit around a black hole. Pure simulation using Einstein's equations alone. And you see, it's a strange swirling imprint in space and time. So I said, these things exist. We have photographs of them. I'll show you a photograph. So this is a simulation. Very strange looking object indeed. About 3 years ago now, 4 years ago, a collaboration called the Event Horizon Collaboration pointed a radio telescope out into the heart of a galaxy called M87, 55 million light years away, and took this photograph. So this is a photograph of one of those things, one of those imprints in the fabric of the universe. Supermassive black hole. This thing is 6 billion times the mass of the Sun, 6 billion times the mass of the Sun, and it's a photograph, and remember, you're looking at a photograph at the end of time. Now we go back to 1974, you might think such a thing has consequences, surely, and indeed it does. And this is where we come to Stephen Hawking's work. So Stephen Hawking, in his own words, calculated that black holes ain't so black. Right? That imprint in the fabric of the universe he found glows. It's a very strange thing. He's saying that space and time themselves have a temperature. That's what he calculated. So important was that discovery, that calculation, that if you go just down the road to Westminster Abbey and look on the floor of the Abbey, you will see this, which is Stephen's memorial stone. And on there, chiselled in stone, literally, on the floor of Westminster Abbey, is that equation, T equals the temperature of a black hole. Why is that so important? Well, it led to a chain of discoveries, a chain of work that's not finished yet, but stretched on for 50 years. The problem is this: it's got a temperature, this thing, this imprint in the fabric of the universe. An imprint in the fabric of the universe having a temperature, what does that mean? If you go back to the 19th century, so when the Albert Hall was being built, a cutting-edge science and engineering was concerned with temperature, steam engines. Wasn't understood what temperature is. It's really a 20th century discovery. Temperature is the jiggling around of things. If something's hot, it means the molecules, the atoms, the building blocks are moving around quickly. That thing is pure space and time, and yet it has a temperature. The suggestion was, and it's now essentially confirmed and understood, the suggestion was that that means that space and time themselves are built of something smaller. We're now beginning to talk in terms of atoms of space and atoms of time, building blocks. Space and time in our new picture, stimulated by this work on black holes, are emergent properties. What does that mean? Well, there's an emergent property with which we're all familiar. It's consciousness, right? Our experience of the world. So we live, we feel, we make music, we do science and art. All those things emerge from a deeper structure. The deeper description of you and me, all human beings, is a collection of atoms. Collections of atoms, hydrogen atoms as old as time, oxygen, iron cut in the hearts of stars, but a pattern, a collection of atoms nonetheless. And out of that emerges this complex phenomenon that we call consciousness. The idea now is that this reality, the space in which we sit and the time that ticks by on our watches, emerges from something deeper. Really beautiful and strange idea. There's a story of Einstein when he was a young boy, and his dad gave him a compass needle, and he looked at the compass. He was 5 years old, and he noticed the compass always points north. And Einstein, being Einstein, he said, this is wonderful, there's some mystery, there's something that I can't see that's driving the universe forward. And later in life, he said, it's a beautiful turn of phrase, he said, what I realised at that moment was that if you study nature carefully, keep pulling on the intellectual threads, then you have a chance of glimpsing something deeply hidden. something deeply hidden, which is the deep underlying structure and beauty of nature. And there's no better example, I think, of that than Einstein would have been so delighted, the study of these things predicted by his theory. Because in studying them, we are glimpsing something deeply hidden, which is the deep structure of reality itself. And that is the story of black holes. Thank you very much.